Hello everyone, thank you for joining me today. In this presentation, we will delve into fascinating worlds of exploratory data analysis, or we call EDA. As we go through the complexities of data, EDA serves as a crucial first step in understanding the underlying patterns and insights that our data holds. By the end of this session, you will have a clear understanding of why EDA is essential in the data analysis process and how it can guide us in making informed decisions based on our findings. So, let's embark on this journey of discovery together. Descriptive analytics. Descriptive analytics is a fundamental aspect of data analysis that focuses on summarizing and interpreting historical data to provide insights into what has happened. Descriptive analytics involve techniques that help describe, show, summarize data in a meaningful way. It aims to answer questions like what is happening by providing a clear overview of the data at hand. There are two main techniques in descriptive analytics. First is data aggregations. Second is data mining. In data aggregation, this process involves gathering data and presenting in a summarized format. For example, an e-commerce company might aggregate data to find the average customer age or the total number of purchases made. This summarized data provides a high-level overview of the datasets. In data mining, this is the analytical part where analysts explore the data to uncover patterns or trends. The outcome of data mining is often visual representations, such as bar graph or pie chart, which help in understanding the data better. The goal of descriptive analytics is to provide insights that can inform decision-making. It allows stakeholders to grasp the current state of affairs and identify trends that may require further investigation or action. Diagnostic analytics is a critical component of data analysis that focuses on understanding the reason behind past events or outcomes. This analytics seeks to delve deeper into data to understand why something happened. Its primary goal is to identify and respond to anomalies or unexpected results within the data. For instance, if there is noticeable drop in sales, diagnostic analytics helps uncover the underlying causes of that decline. Diagnostic analytics isn't just about fixing problems, though you can also use it to see what's driving positive results. Various techniques can be employed in diagnostic analytics, including first, probability theory, regression analysis, filtering, and also time series analysis. For example, if descriptive analytics reveals a 20% drop in sale for a particular month, the next logical step is to conduct a diagnostic analysis to determine the reason behind this decline. Analysts will look for additional data sources that might provide insights into the factor contributing to the sales drop, such as changes in marketing strategies, customer feedback, or external market conditions. In summary, diagnostic analytics plays a vital role in data analysis process by helping organizations understand why behind their data, enabling them to respond effectively to both challenges and opportunities. Predictive analytics is an advanced form of data analysis that focuses on forecasting future outcomes based on historical data. Predictive analytics involve the use of data, statistical algorithms, and machine learning techniques to identify the likelihood of future outcomes. Primary goal is to go beyond merely understanding what has happened in the past to providing insights into what is likely to happen in the future. This helps organizations make proactive decisions based on predictions rather than reactive ones. Predictive analytics employs various methods, including statistical algorithms, which are the mathematical models that analyze historical data to identify patterns and relationships that can be used for forecasting. Also use machine learning techniques, which involve training algorithms on historical data to improve their accuracy in predicting the future events. Machine learning models can adapt and learn from new data, enhancing their predictive capabilities over time. For example, a retail company might use predictive analytics to forecast sales for the upcoming quarter based on the past sales data, seasonal trends, and also economic indicator. The outcome of predictive analytics is a best assessment of future events, allowing organizations to anticipate changes and trends. Next is prescriptive analytics. Prescriptive analytics is the most advanced types of data analysis, focusing on providing recommendations for actions based on data analysis. This technique analyzes data to provide actionable recommendations on how to optimize businesses' practice for various predicted outcomes. It goes beyond simply predicting what might happen, as in predictive analytics, to suggesting the best course of action to take in response to those predictions. Prescriptive analytics employs a combination of algorithms, machine learning, statistical methods, and also computational modeling. For algorithms, these are sets of rules or calculations that help in processing data and generating recommendations. For machine learning, a technique allows models to learn from data and improve their recommendations over time. For statistical methods, this method helps in understanding data distributions and relationships, which are crucial for making informed recommendations. And lastly, computational modeling, which involves simulating different scenarios to evaluate potential outcomes based on various decision pathways. For example, if predictive analytics indicates a potential drop in sales, prescriptive analytics might recommend specific marketing campaigns or adjustment in pricing strategies to counteract that decline. Exploratory data analysis (EDA) is a crucial step in the data analysis process that focuses on understanding the dataset being used. It involves using various techniques to better understand the characteristic and structure of a dataset. The primary goal is to extract important insights, identify patterns, and uncover anomalies before proceeding with more formal analysis. EDA encompasses several techniques, including extracting important variables. This involves identifying which variables in the datasets are relevant for analysis and which can be disregarded as irrelevant or redundant. The second technique is identifying outliers and missing values. The analysts look for data points that deviate significantly from the rest of data, which is what we call outliers, and check for any missing values that could affect the analysis. One is understanding relationship between variables. EDA helps in exploring how different variables interact with each other, which can reveal correlations or dependencies that are important for further analysis. Lastly is visualizations, creating visual representations of data such as histogram, scatter plots, and box plots, which helps identify trends, distributions, and also relationship visually. EDA is typically performed at the beginning of the data analysis process. For example, before building predictive models, analysts will conduct EDA to ensure they understand the data structure and quality. This step helps in making informed decisions about data cleaning, transformation, and also the selections of appropriate modeling techniques. The outcome of EDA is comprehensive understanding of dataset, which maximize insight and minimize potential errors in subsequent analysis. The components of exploratory data analysis (EDA) are essential elements that help analysts understand and prepare their datasets for further analysis. First, they need to understand the variable, which involve gaining insights into different variables present in the datasets, including their types, distributions, and the role they play in the analysis. Analysts assess the significance of each variable and how they're related to the overall dataset. Next is data cleaning. This process includes identifying and handling missing values, correcting inconsistencies, and removing duplicates or irrelevant data points. Next is analyzing relationship between variables. This can include examining correlation, dependencies, and potential causal relationships. Lastly is visualizations. Although not explicitly listed in the components, visualizations are a fundamental part of EDA, creating visual representations of the data, such as scatter plots, histogram, and box plots, allow analysts to quickly identify trends, distributions, and outliers, making it easier to interpret the data. These are the list of the techniques used in EDA. Descriptive statistics. It's a branch of statistics that focus on summarizing and describing the main features of dataset. It provides a way to present quantitative descriptions in a manageable form. Techniques involve the analysis of data that helps to describe, show, or summarize data in a meaningful way. Descriptive statistics typically include several key measures, which can be categorized into different types. First, to measure central tendency. For example, mean. Mean is the average value of the dataset, calculated by summing all values and dividing by the numbers of observation. Next is median. Median is the middle value when the data is ordered, representing the 50th percentile or the second quartile. First quartile, 25th percentile, indicating that 25% of the data falls below this value. Third quartile, the 75th percentile, indicating that 75% of the data falls below this value. Minimum is the smallest observation in the column, and maximum is the largest observation in columns. Descriptive statistics is used in various fields to summarize data and provide insights. For example, in business, it can help summarize sales data to understand performance trends. In healthcare, it can summarize patient data to identify common health issues. The outcome of descriptive statistics is a set of summary measures that provide a clear and concise overview of the dataset. This summary helps analysts and decision makers understand the data's characteristics, identifying patterns, and make informed decisions based on the insight gained. Univariate analysis plots are graphically representations used to analyze and visualize the distributions and characteristics of a single variable in a dataset. These plots help in understanding the underlying patterns, trends, and anomalies within that variables. This slide shows plots which can be used for numeric variable analysis and also for categorical variable analysis. The univariate analysis focuses on examining one variable at a time. The primary goal is to summarize and visualize the distributions of that variable, allowing analysts to identify patterns, central tendencies, and variation within the data. A box plot, also known as a whisker plot, it is a standardized way of displaying the distributions of a data based on a 5-number summary. It provides a visual representation of the central tendencies, variability, and potential outliers in the data. A box plot consists of several key components which has discussed before, which is first minimum, first quartile Q1, median Q2, third quartile Q3, maximum, whiskers. Whiskers is a line that extends from the box to the minimum and maximum values, showing the range of the data. And lastly, outliers is the data points that fall outside the whiskers, typically defined as the values that are 1.5 times the interquartile range, what we call it IQR, above Q3 or below Q1. Outliers are often represented as individual points on the plot. The box plot provides a visual summary of the data distribution. As you can see in the figure, the lengths of the box represent the interquartile range, IQR, which indicates the spread of the middle 50% of the data. The positions of the median line within the box shows the central tendency of the data. And lastly, the whiskers indicate the range of the data, while the presence of outliers can highlight unusual observations that may require further investigations. A violin plot is a data visualization tool that combines the features of a box plot and kernel density plot. It provides a comprehensive view of the distributions of numeric variable, particularly useful for understanding the underlying distribution shape, especially in case where the data may be multimodal, which having multiple peaks. A violin plot consists of several key components. First is box plot element. Second is density estimation, and the third one is multiple peaks. Like a box plot, a violin plot typically includes a box that represents the interquartile range IQR with a line indicating the median. Density estimation, which is the side of the violin plots are shaped like violins, representing the kernel density estimation KDE of the data. This shows the probability density of the variable at different values, allowing for visual representations of distribution shapes. Then you have multiple peaks, which is the width of the violin at different values, indicate density of data points. Wider sections suggest a higher concentration of data points, while narrower sections indicate lower concentration. Violin plots offer several advantages over traditional box plots. First, they provide more information about distribution shape, allowing for a better understanding of the data characteristic. Secondly, they are particularly useful when dealing with complex datasets that may have multiple modes, as they can reveal patterns that box plot may not capture. Violin plots are widely used in various fields, including statistics, biology, and also social sciences, to visualize the distributions of continuous variables across different categories or groups. Next is scatter plot. Scatterplot is a graphical representation used to display relationship between two quantitative variables. It is a fundamental tool in exploratory data analysis, allowing researchers to visualize potential correlation, trends, and patterns in the data. The scatter plots consist of following key components. First is axis, which is the horizontal axis x-axis, represent one variable, while the vertical axis y-axis represent the other variable. Each axis is typically labeled with the variable name and its units of measurements. The next key component is data point. Each point on the scatter plots correspond to an observation of the dataset, with its position determined by the values of two variables being plotted. For example, if x variable is height and the y variable is weight, each point represents an individual height and weight. Scatter plots allow the visualizations of relationship between variables. First is positive correlation. If the points tend to rise together, for example, one variable increases, the other also increases, the relationship is considered positive. Second is negative correlation. If one variable increases while the other is decreases, the relationship is negative. Next is no correlation. If there is no discernible pattern or trend in the data points, the relationship is considered zero or weak. Scatter plots provide a clear visual representation of relationship between two variables, making it easy to identify trends and patterns. Grouping data is a technique used in data analysis to organize and summarize information based on specific categories or characteristics. This method allows analysts to gain insight into relationship between different variables and to understand how certain factors influence outcomes. The primary purpose of grouping data is to simplify complex data sets by categorizing them into meaningful segments. This helps in identifying patterns. By grouping data, analysts can identify trends and patterns that may not be apparent in the raw data. Second one is comparative analysis. Grouping allows for comparison between different categories, making it easier to analyze how different groups behave or perform relative to one another. An example provided in the slides involves analyzing the average price of apartments based on their features, such as whether they have garage or central air conditioning. By grouping the data according to this feature, one can observe how the sale prices differ across various combinations of these attributes. Missing values are those rows or columns which have no data recorded in particular observation. Analyzing this value is important as this may lead to weak or biased analysis. We can handle missing values in many ways. First is deletion. The drop now function method from Pandas library can be used to delete rows or entire columns. Second one is imputation. Instead of deleting data, imputation involves replacing missing values, help retain more data while addressing the issue of missingness. The next one is predictive filling. This method uses interpolation techniques to estimate and fill in missed linear interpolations or other methods to fill in gaps. Properly addressing missing values is essential to ensure the integrity for the analysis. Ignoring or improperly handling missing data can lead to incomplete and affect the overall quality of the insights derived from the dataset. A heat map is graphical representation of data where individual values are represented as colors. It is particularly useful for visualizing complex data matrices and can help identifying patterns, correlation, and missing values. In the context of handling missing values, a heat map can visually indicate the presence of missing data within a dataset. This allows analysts to quickly assess the extent and distributions of missing values across different variables. Correlation quantifies the degree to which two variables move in relation to each other. It helps to understand how changes in one variable may affect changes in another variable. A correlation of 1 indicates a perfect positive correlation, meaning that as one variable increases, the other variable also increases proportionally. A correlation of -1 indicates a perfect negative correlation, meaning that as one variable increases, the other variable decreases proportionally. And lastly, zero correlation indicates no linear relationship between two variables, suggesting that changes in one variable do not predict changes in the other. For example, smoking is correlated with lung cancer. This illustrates how one variable, which is smoking, is known to increase likelihoods of another variable, which is lung cancer, highlighting the practical implications of understanding correlation in real-world scenario. In conclusion, exploratory data analysis is a vital process in data science that enables analysts to clean, visualize, and understand their data. By employing various EDA techniques, analysts can uncover valuable insight, identify potential issues, and prepare their datasets for further analysis. Mastery of EDA is essential for anyone looking to drive meaningful conclusions from data and make informed decisions based on their findings. Thank you for listening. See you in the next chapter.